Dr. Diaz, and today we are going to explore a set of tools that chemists use to connect the microscopic world of atoms to the measurable world around us. We will begin to look at formula mass, molar mass, two ideas that help us to quantify how heavy a substance is, whether we are talking about a single molecule or entire moles of particles. From there, we will examine mass percent composition, which tells us how much of each element makes up a compound, and help us compare substance or identify unknown samples. Then we're going to go to empirical formula. That is the simplest ratio of atoms in a compound, and how that relates to the molecular formula, which shows the actual number of atoms that contains in each molecule. So together, these concepts from the foundation of quantitative chemistry and allows us to translate chemical formulas into real, meaningful informations. So let's start over here. So formula mass is the mass of an individual molecule or formula unit, also known as molecular mass or molecular weight. So what is the difference between formula mass and the molar mass? So formula mass, we talk about atomic mass unit. So we're gonna do the same thing. We sum the mass of atoms in a single molecule or formula unit. So we're gonna obtain the whole, which is sum of the part. So like water molecule over here, so I have 2 atoms of hydrogen, and we know through the periodic table the atomic mass unit is 1.01 per atom of hydrogen. And we have 1 atom of oxygen, and we do know that 1 atom of oxygen weighs 16.00 atomic mass units. So we add all together and we have the atomic mass unit, which is 18.02 grams. So the molar mass, you're going to do the same thing. But the molar mass of compound is expressed in grams per mole. And it has the same numerical value as the formula mass, because we're going to calculate the same way, right? So, but this applies to macroscopic quantities. So allowing us to convert between grams, moles, number of particles, all this, because we're going to use grams per mole. So to calculate, you're going to use the same method that we use to calculate the formula mass. We're going to count the atoms in each molecule and times the atomic mass unit of each atom. And then we're going to add all together. Don't forget to add the units, grams per mole. So, and we're going to use the grams per mole to find everything that we need. Imagine if you need to convert mass to molecules. So, you know, to convert to molecules, I know that 1 mole contains 6.02 times 10^23 units, molecules, particles, atoms, right? So, but pay attention, it's 1 mole. Don't say that grams. Remember, grams is different for each element. You know that 1 mole of oxygen contains 16 grams. 1 mole of hydrogen contains 1 gram. So it's not possible to go directly from gram to molecules, sorry. So this way over here is not possible. So first we need to convert to moles using the molar mass. And then you can use Avogadro over here to find molecules. Okay? So that is the way that you're going to do, and you're going to do in stoichiometry. Another very important thing is the composition of compounds. And it's really important, and you already do this during your day and your life, right? Because chemical formula in a combination with the molar mass of its constituent elements indicate the relative quantity of each element in a compound. Let's give an example that you do every single day. Imagine if I have a beverage that has 180 grams of water and 20 grams of sugar. So I can translate this for someone like, okay, in the total I have 200 grams of this beverage over here, right? So I know that I have 20 grams of sugar. And if you divide by the total, and multiply by 100, because I want a percentage, I'm going to have 10%. So 10% of my beverage is sugar. So this is the same thing that we're going to do for any compounds. For example, if I have water, I know that I have, in this case, 2 grams of hydrogen and atomic mass units of oxygen, 16, right? Grams of oxygen. So the total, I have 18 grams. If I divide the hydrogen, I'm going to have 2 divided by 18. And if you multiply by 100, I'm going to have the percentage of hydrogen in this water molecule. If I do this with the oxygen, I'm going to have the same, the percentage of oxygen in that water molecule. This is how we're going to do always. So the mass percent in an element is equal to the mass of element divided by the mass of 1 mole of the compound. So it's always part divided by the total multiplied by 100. So let's test your understanding over here without doing any calculations. List the elements in C6, H6O, and order of decreasing mass percent composition. So we know that we're going to divide part by the total and times 100 for each atom. And we know, if you have the periodic table in your hand, that the heaviest one that we have here is oxygen. This is the heaviest. This is the one that weighs more because you have 16 grams. And then comes the carbon, is the second one. But look at this, carbon I have 6. Even though that is only 12 grams, I'm gonna have 6 of this. And the hydrogen is the lighter one, which has a mass of 1 gram. So I know, without doing any math, that carbon will have a higher percent composition than oxygen, and oxygen will be higher than hydrogen, right? So this is easy, this is not hard, and that's it. The only thing that you need to know is mass percent composition. You only divide the part by the total and multiply by 100. So like in chemical formulas, I can use the percent composition as a conversion factor. And actually we do this with everything that we learn in chemistry, right? So if I talk about molar mass, I can use molar mass as conversion factor. I can use Avogadro as conversion factor. So, and this will not be different. So the ratios can be used as conversion factor between mass of element and the mass of the compound. So if you look to this, let's test again your understand over here. So the molecular formula of water is H2O, and you know that. Which ratio can be correctly derived from this formula? And explain. So look at those alternatives that we have over here. I will ask you to think a while, pause your video, and then answer by yourself. Okay, so in the first alternative, you have 2 grams of hydrogen per 1 gram of water. Cannot beat this, right? Because remember, in chemistry, we need to work with moles. I cannot say that because in the in grams, because look, in the water molecules, I don't have 1 gram of water and 2 grams of hydrogen in 1 gram of water. Remember, to find the total grams over here, I need to the moles. Like I know that 1 mole of hydrogen contains 1 gram, 0.1. So if I multiply by 2, I have 2 grams, 0.02 grams of hydrogen, and I'm gonna have 1 atom of oxygen, but I have 16 grams in 1 mole. So I'm gonna have 16 grams of oxygen. So I don't have 2 grams of hydrogen and 1 gram of water, so this cannot be it. So volume. So volume depends of a lot of things. Density, pressure, temperature. So I cannot say that the volume will be the same. So I cannot work with this. And this says that I have 2 mole of hydrogen and 1 mole of water molecule. That's correct, right? Because we work with the mole. So I know that 1 mole of water molecule, I have 2 moles of hydrogen and 1 mole of oxygen. So that is the only correct way here. Okay, so pay attention that we always work with moles. So empirical formula is simplest whole number ratio of the atoms or mole of elements in a compound, not a ratio of masses. Look what that means. Imagine if I have C4H8. I can divide both numbers by 4, right? So I'm gonna have 6H2. So that is the smallest number. I could say that is my molecular formula, and this is my empirical formula because I have the smallest quantity over here. So that is the simplest whole number ratio. That doesn't represent the real molecule, the real quantity of each atom in the molecule, but that is the simplest number ratio. So can be determined from elemental analysis through percent composition or masses of elements formed when a compound is decomposed or that reacted together to form a compound. So let's practice a little bit because this is the only way to understand better how to get the empirical formula, how that works. And the first step goes through the steps that you need to do it, to go over to get the empirical formula. So first, we need to convert percentage to gram. That means some problem is going to give you the percentage, and then you need to convert to grams. And how are you going to do that? So you're going to take in consideration 100 grams of the compounds. Imagine if it tells you that I have 70% of oxygen and 30% of hydrogen in some compounds. It's just an example that doesn't exist, just an example, okay? So if I consider 100 grams, I'm gonna have 70% of oxygen would be 7 grams, right? And if it's 30% of hydrogen and 100 grams, so 30 grams. So you only convert directly. Good. And then if it's in percentage, you don't need to do anything. It's already mass, that's okay. You don't need to do anything. But then you need to convert grams to moles. And how are you going to do this? Using molar mass as your unit factor, a conversion factor. And then you're going to find the moles. Remember, you cannot use grams to find anything. First, you need 2 grams to convert to moles, and then you can go ahead in your calculations. And then you're going to write the pseudo formula using calculated moles as subscript. However, it's not the end. So you need to find which one is the smallest number of moles, and then you divide both or 3, because molecule can have more than 3, right? More than 2 atoms together. So you're going to divide all by the smallest number of moles. If the result is within 0.1 of whole number, you can round to whole number. For example, if it's 2.1, I'm going to say that is 2. But if you have numbers like 0.5, for example, I have a formula here which I had 0.5x and 1y. So I'm going to multiply all by 2, and my final formula is going to be this, right? So you don't need to write down the 1. I mean, just write down because I'm showing you what I did over here. Multiply all. So if the ratio is 0.33 or 0.67, you're going to multiply all by 3. If the ratio is 0.25 or 0.75, you're going to multiply all by 4. Skip if the ratios are already whole numbers, okay? So let's press a little bit over here. So a compound is found to be 53% aluminum and 47% of oxygen. So you're going to find out the empirical formula. How are you going to do? Pause your video and try by yourself. So first, you're going to convert to grams. Assuming that sample weighs 100 grams, there would be 53 grams of aluminum and 47 grams of oxygen, right? So then we need to convert to moles, and you're going to use the molar mass. That's why you need your periodic table. So I have 53 grams of aluminum. So, and I know the molar mass of aluminum is 27 grams of aluminum. Okay, I know that in your periodic table, probably you're gonna see 26.98. I round the numbers here just to make my life easier. But you will not do this in exam. You're gonna use all the numbers that you have and the periodic table that I'm gonna provide to you during the exams, okay? So then I can cancel out those units and they're gonna have moles of aluminum. So 53 divided by 27 is 1.96 moles of aluminum. And then I'm gonna do the same thing with oxygen. So I have 16 grams and 1 mole of oxygen. This is the molar mass. And then I'm gonna divide this by 16 grams and I have 2.94 moles of oxygen. So now you're gonna divide both by the smallest number. And I know that the smallest number here is 1.96 because I'm going to compare both, right? So you're going to divide both by the smallest number and you're going to have the ratio over here, right? 1 and 1.5. Remember, if it's 0.5, what I'm going to do here? Multiply by 2. So then you're going to have a whole number. So this is my final formula. Aluminum 2, oxygen 3. Those, the subscript over here, you will never change. Okay, so if it tells you that I have a 2 aluminum O3, I have 2 molecules of this. I cannot multiply like, okay, I have this. This is what I have. No, this is a completely different monster. And I can explain to you what I mean. So this is the calculation of empirical formula. Right? So I have the simplest numbers over here, and this is my molecule over here. If I want to tell you that I have 2 molecules of this, I'm going to use this. I have 2 molecules of this. I will not multiply all again, okay? So because if it tells you, okay, my formula is this, 2 eyes, 1 nose, 1 mouth. That's a face. 2 eyes, and 1 nose and 1 mouth. Okay, so if I have a 2, I'm gonna do this. I have a 2 face. But if I don't know too much chemistry, but I think I can do this. E4 and 2 and 4 maybe 2. So I multiply the atoms like this, and what you're gonna have at the end is this, a complete different monster, right? Look at this. I have 2 face, and here I have a monster. So those subscript here tells me how many atoms I have a molecule. So like water, I have 2 hydrogen and 1 oxygen. So if I want to tell you that I have 2 water molecules, I'm gonna do this, 2 water molecules. I will never do this because this is a completely different monster. Okay? It's just a parenthesis here, and there's empirical formula just to explain what is a subscript means, is the number of atoms in a molecule. Here we do all these calculations and we multiply, we have whole numbers to obtain the empirical formula. That's the empirical formula, okay? Let's test your understanding here how to obtain the empirical formula. So here we have a problem that compound containing nitrogen and oxygen is decomposed in the laboratory. It produces 24.5 grams nitrogen and 70 grams of oxygen. And it asks you to calculate the empirical formula of the compounds. So here you already have grams, so you don't need to convert percentage to gram because you already have in grams. So pause your video and try by yourself. So first you have to find the empirical formula. So first you're going to convert all the grams and moles. So you're going to use molar mass of each element to find the moles. So we have the mass of each element times the conversion factor of the molar mass, and you're going to find the moles. Then you can write down the pseudo formula of the compound using the moles that you calculated over here. So now you know that you need whole numbers. I cannot let like this. So, but first you need to divide by the smallest number of moles each of the atoms. And this, what you got? Nitrogen 1 and oxygen 2.5. You cannot leave like this because we need whole numbers. You will never see a formula with those numbers like this, right? So if it's 2.5, I can multiply by 2 both of the elements, and this is my final formula. So to get the whole numbers, you can have this in your mind, like if it's 0.20, you're going to multiply by 5. If it's 0.25, you multiply by 4. If it's 0.50, you multiply by 2. Okay? So to get the whole numbers. To practice more, I suggest you to try to solve this problem over here. The final answer is over here. If you cannot get there, and if you still have questions, I invite you to watch the resource that I left for you on Canvas. Resources are short videos from different authors, different professors that explain the same thing. If you still cannot do it, just send me an email or ask me questions. I'm gonna record a video like very short videos, step by step, to explain again. So don't worry, I'm here to help you to grow, to learn. And if you have a question, you're free to ask me. And how are we going to find molecular formula? So the molecular formula is a whole number multiple of the empirical formula. So that will tell you exactly the numbers of each atoms we contain in the formula. Okay? And to find out the molecular formula, you need to know the empirical formula and the molar mass of the compound. So what you're going to do is divide the molar mass of the empirical, the molar mass of the molecular formula by the empirical formula molar mass. And then you're going to find a ratio that you're going to multiply by, imagine if I find like here 2, and my empirical formula is this. So if my ratio over here is 2, what I'm going to do is multiply all by 2, and I'm going to have this. This is my molecular formula. Let's see this on practice. So here I have a problem with the butadiene, which is the component responsible for the smell and taste of butter and cheese, and it contains the element carbon, hydrogen, and oxygen. And this is the empirical formula. So, and its molar mass, it's over here. So I have the molar mass, and I have the empirical formula. So what do you need to do? First, I need to find the molar mass of my empirical formula, right? Because I have the molar mass of my molecular formula. So what I'm going to do is to find that. So I'm going to find the molar mass. I have already the molar mass, and I just need to calculate the formula, the molar mass of empirical formula. So then you're going to solve that, right? So what I have here is the molar mass of my empirical formula. I have 2 atoms of carbon, 3 of hydrogen, and 1 of oxygen. So here's oxygen, hydrogen, and carbon. So that is my molar mass of empirical formula. So now we're going to divide the molar mass of my molecular formula by the empirical formula, which is 2. So now I only need to grab the empirical formula, multiply all by 2. See, this is my result. And we can check the answer. You can find out the molar mass of this and match with the molar mass given by the problem. So you're right. So for practice, you can try to do those 2 suggested problems over here. Again, if you don't still confident, if you still are not confident, if you still have questions, it's normal. So please ask me questions, okay? And let's go to reactions. Let's analyze combustion analysis. Like a common technique for analyzing compound is to burn a known mass of compound and weigh amounts of products. This is generally used for organic compounds containing carbon, hydrogen, and the oxygen. By knowing the mass of the products and composition of the constituent elements in the product, the original amount of the constituent elements can be determined. All the original carbon form CO2. The original hydrogen form water. And the original mass of oxygen is found by subtraction. So once the masses of all the constituent elements in the original compound have been determined, the empirical formula can be determined. So we have equipment like when we burn the compound. So the film gonna pass over here. So here we have the water absorbed. So I will not have moisture over here. And then the water and carbon dioxide produced are isolated. So we have the CO2 absorbed here. So water goes in the first level and first step, and then the CO2 is be absorbed in the second stage of the equipment, and then some other substance will be eliminated because it will not be absorbed over here, not eliminate, but it will come out from this part over here. So let's see this on practice, on problems that you're gonna need to solve some tests or assignments. So we have a combustion over here, and the compound containing only carbon and hydrogen produce 1.83 grams of CO2 and 0.901 grams of water. And the problem is asking us to find the empirical formula. How are we going to do this? So first, we check what we have. We have the mass of two compounds, right? And we need to find the empirical formula. So first we need to convert the mass to moles by using the appropriate molar mass of each compound, right? So we're going to find the moles of carbon dioxide and the moles of water using the molar mass of as conversion factor, right? So in the second step and the third step, you're going to convert the moles of carbon dioxide and the moles of water to moles of carbon and the moles of hydrogen. So we're going to use the conversion factors again. So I have in the CO2 molecule, I have 1 mole of carbon for 1 mole per 1 mole of CO2. So if I use the moles of CO2, I'm going to find the moles of carbon. And they're going to do the same thing with water. So I have 2 moles of hydrogen and 1 mole of water, right? So I have 2 moles of hydrogen and 1 mole of water. So I found the moles of hydrogen. Now, in the fourth step, if the compound contains an element other than carbon and hydrogen, we need to find the mass of the other element, right? By subtracting the sum of the mass of carbon and hydrogen from the mass of the sample. Finally, we're going to convert the mass of the other elements to moles. Look at this. So the sample contains no elements other than carbon and hydrogen. So proceed to the next step. So write down the pseudo formula for the compound. Use the number of moles of each element that you found out. So this is the moles of carbon that we found out and the moles of hydrogen that is over here that you just calculated. So now we're going to divide both by the smallest number, right? So the smallest number is 0.0416. So divide both, and this is what I have over here. So what are you going to do now? So I need a whole number. So to have a whole number, we're going to multiply all the subscript by whole number to get whole number subscript. So we're going to multiply by 5. So I can have my whole numbers over here. So that's it. That's all on this. It's kind of the same thing that we did in the empirical formula, but here we have a reaction. So we have the whole molecule, and then we need to find out the single element like we did before. In this case, the problem shows us that we only have carbon and hydrogen. So if you only have the carbon and the hydrogen, the only thing that you need to find is how many carbons I have in the molecule and how many hydrogen I have in the molecule. So you're going to find out, and then follow the steps that you just did in empirical formula. Okay? And just for practice, here is another suggestion for you. So try to do by yourself this one, and I'm giving you the answer, the correct empirical formula that you need to find out. And if you're not able to solve, don't worry. Just review the class or go to the resource, and then if you are still not getting there, just ask me questions. Okay, I will help you. So organic compounds, early chemists would divide compounds into two types, organic and inorganic. And since we talk about the carbon and hydrogen and combustion over there, it's important to talk a little bit about the organic compounds. Compounds originating from living things were called organic. Compounds originating from earth were called inorganic. Organic compounds were easily decomposed and they could not be made in the lab. However, some scientists already did this, and they could make the urea in the lab. So that was like break a little bit of this part of it. It's all natural living things. Okay, inorganic compounds were very difficult to decompose, but could be synthesized. So the modern organic compounds, we know that today organic compounds are commonly made in the lab, and we find them all around us. Organic compounds are major components of living organisms, like us or anything. So we have a lot of carbon and nitrogen, hydrogen, composed of mainly carbon and hydrogen, right? Of oxygen, nitrogen, sulfur, and trace amounts of other elements. The key element of organic chemistry is carbon. That is the star of organic chemistry over here. I'm sorry. So, and most of the medications that we take is organic compounds, okay? So carbon bonding, how they bond. So carbon atoms bond almost exclusively covalently. So covalent bonds. They share electrons, okay? Compounds with ionic bond carbon are generally inorganic. When carbon bonds forms 4 covalent bonds, including single, double, or triple bonds. Could be carbon with hydrogen for single, or could be carbon with the carbon and more hydrogens over here, right? 1, 2, 3, 4. So the most important here is to have stability. So to be stable, carbon need 4 bonds. Carbon is unique in that and it can bond with itself and form limitless chains of carbon atoms. Like I could have octane, which is 8 carbons, like part of the gasoline that you use as fuel, right? And a bunch of hydrogen around over here. Or could form a ring over here with double bonds and more hydrogens around. So this is how carbon works. So we have here another examples like propane, isobutane, cyclohexane, ethane, ethyne, acetic acid. All those are organic compounds. And hydrocarbons are one of the most important in my field, like petroleum, fossil fuels, and also in medications. Organic compounds can be categorized in 2 types. We have hydrocarbons and the functionalized hydrocarbons. What is that? Hydrocarbons is only carbon and a hydrogen. So they are organic compounds that contains only carbon and hydrogen, like oil, gasoline, liquid propane, and natural gas. Hydrocarbons compose common fuels, as I said before. So, and to name, it's really pretty easy. So hydrocarbons contain only single bonds that we call alkanes, and if they contain double bonds, we call alkenes, or triple bonds, alkynes. So we use always the number of carbon we need to count. So you need a prefix like methane, so I only have 1 carbon. Ethane, I have 2 carbons. Propane, I have 1, 2, 3 carbons, so this is why it's prop. Butane, so like if you have a 4, so butane. So pent, if you have 5, X, and it goes on. So the base name for a number of hydrocarbon I listed. So base name determined by the number of carbon, and suffix determined by presence of multiple bonds. So here I have another examples like methane here, carbon and hydrogens. That's the structural formula, a space filling model. That is primary component of natural gas, and you have several other components that you're gonna see with more details in organic chemistry. Okay, the functional groups derives from the functionality of or chemical character that is specific atom or group of atoms import to an organic compound. So a group of organic compounds with the same functional group will form a family. Like here, we have the hydroxyl functional group. So we have alcohol over here. So in here, the same thing, I have this functional group. So all the other elements is carbon and hydrogen. So here I have a methanol and here isopropanol. So we have different functional groups. Besides alcohols, I have ether, aldehydes, ketones, carboxylic acids, esters, amines. So all these are functional groups. You will see better with more details in organic chemistry. That's it. That's all. Bye for now.